Hello everyone, welcome to the OneClass channel. My name is Marlyn. I'm a second year student at the University of Waterloo studying chemical physics with a math minor. Today I'm going to be working through some high school and college level chemistry problems. Be sure to check out the links in the description if you're in need of any extra homework help or would like some one-on-one tutoring. Okay. So for our first question, we're going to be looking for the Lewis formulas of the following. And so we start by counting the valence electrons. We have 2 from beryllium and 2 by 7 from the fluorine, and then we don't have any charges. So that is just going to give us 2 plus 14. So we have 16 electrons to manage. Let's go ahead and label these. This is from beryllium, and this is from the 2 fluorines. Okay, and so we start with a skeleton that looks like that. Let's go ahead and add 1 bond in between them and the necessary valence electrons around the fluorines. Let's count to see if we hit the 16. So 2, 4, 6. We have 6 by 2 plus 2, 4. So 12 plus 4, and that's going to give us 16, which means we have covered all of the electrons. And so this is allowed because in this scenario we have an underfilled octet for beryllium. So let's just go ahead and note that down. Additionally, let's check our formal charges to make sure that it all makes sense. So for the fluorines, we will have F, and that is going to be 7 valence electrons, minus each of them have 6 non-bonding electrons, and only 2 bonding electrons, so 2 over 2. And that is going to give us 7 minus 6 minus 1, which is going to give us a formal charge of 0. On the beryllium, we're going to have 2 minus 0 non-bonding electrons, minus 2, 4, so 4 over 2 bonding electrons, and that's just going to give us 2 minus 2, and that is also 0. So the formal charges check out, valence electrons check out, which means that this is going to be our final structure. Move on to the next one. That is BeF3 minus. Let's go ahead and count the valence electrons. So we have 2 from the beryllium plus 3 by 7 from the fluorines plus 1 because of the charge. Let's go ahead and label those. So this is BeF3 minus. And so that's just going to give us 3 plus 21. So we have 24 electrons to manage. So we start with just the skeleton of this, and 1 bond on each. Let's fill in our valence electrons on each of the fluorines, so fill their octets. Okay, and then let's see if we hit the 24. So we have 6 on 3 of the fluorines, plus 2, 4, 6, so 3 by 2. And so that is going to give us 18 plus 6, and that is indeed our 24. So you see all of the electrons have been managed here. And so let's go ahead and check our formal charges. And again, this is going to be allowed because the beryllium will again have an underfilled octet. So now let's go about checking the formal charges. So again, it's the same formula of valence electrons minus the lone pair electrons minus the bonding pair over 2 electrons. And so for each of the fluorines, that will give us 7 minus 2, 4, 6 lone pairs on each of them, minus 2 electrons in a bonding pair for each of them. And that is just going to give us 7 minus 7, which would give us 0. Let's check in on our beryllium. 2 valence electrons, minus it has 0 lone pairs, minus 2, 4, 6 bonding pair electrons. And that is just going to give us 2 minus 3. And that's going to give us -1. In this scenario, that does make sense. We're asked for this, and it has the negative charge here. So the negative charge is being caused by the beryllium. And that is going to be our final answer. The formal charges make sense, and the valence electrons make sense. On to our next one. ER3. Let's go ahead and check on our valence electrons. And so we have 3 plus 3 by 7. And so that's going to give us 3 plus 21 again. And that's going to give us 24 electrons to manage. We can go ahead and just label them. So this is caused by the aluminum. This is caused by the 3 bromines. And so let's start with our skeleton structure. And start with 1 bond on each and filling in the octets of our halogens. Okay, count our valence electrons. We will have 6 by 3 plus 2, 4, 6. 6. That is going to give us 18 plus 6, which again will give us the necessary 24. And so again, this will be allowed because aluminum will have an underfilled octet. Let's go ahead and count our formal charges. Let's just write down the formula very quickly. And so for our aluminum, that is going to be 3 minus 0 minus 6 over 2. And that's just 3 minus 3, which is 0. For our bromines, that is going to be 7 minus 6 on each of them, minus 2 over 2. And that's going to give us 7 minus 7, which is again 0. And that again makes sense because we had a net charge of 0, which is allowed according to the formal charges we have on each of them. And so this is going to be our final structure again. And those are our final answers. Okay, next up we are looking for the balanced equation for the dissolution of calcium carbonate. So because of the fact that it's a strong electrolyte, it's going to completely ionize in water. So if you write that out, we have CaCO3 plus H2O, and the reaction goes to completion. And so these ions will separate into the solution. Sorry, so we get Ca2 plus ions in there, plus the carbonate ions too. So this is also in aqueous. Plus we have the OH ions that will come from the water, plus the hydronium ions. So the hydrogen ions also coming from the water. And then we just need to note that OH minus aqueous plus H plus. Aqueous is the same thing as just liquid H2O. So we can rewrite this as liquid H2O. And because of that, these two will cancel. And so what it should actually look like would be CaCO3 solid to become the calcium ions plus CO3 minus ions. And that is going to be your final answer. For our next question, we want to draw the Lewis structure for ClO and include all lone pairs of electrons. So as usual, we begin by counting the valence electrons. We are going to have 7 from the chlorine and 6 from the oxygen. That is going to give us 13 electrons. And then we can just note here that we have an odd number of electrons and no charge. This would imply that we're going to have radicals. And these are just going to be single electrons, which are typically unstable, and so you don't see them that often. And so let's first go about the skeleton structure. Let's use 1 to connect them. Fill in our octet, and then let's see if this equals our 14. So we have 6 by 2 plus 2. So 12 plus 2, and that's going to be 14. So we have an extra electron here. We can decide to get rid of the one on Cl, and that will leave us with that. And then let's go about checking our formal charges. So we can just write down the formula. Minus the lone pair of electrons minus the bonding pair over 2 of electrons. And so for chlorine, that is going to be 7 minus, it has 5 lone pairs of electrons, minus 2 over 2. So that's going to be 7 minus 6, which is going to give us positive 1. Let's check on the oxygen. It is going to give us 6 minus 2 over 2. That's just going to give us 0 minus 1, and that's going to be a negative 1 charge. And so if we leave it like this, we have a negative charge and a positive charge on the chlorine. And yes, it's optimized in the sense that we do have the more negative charge on the oxygen, but we can decide to get rid of both of these charges if we include a double bond. And the reasoning for this is because we like to minimize charges on our Lewis structures, and if that's possible without compromising our valence electrons, then it's best to do so. And so let's write out what we have just spoken about. And that will leave us like that. Let's just double check on our valence electrons. So we have 3 plus 2 by 2 plus 2, 4. And so that's going to be 3 plus 4 plus 4. And that's going to be 8 plus 3, which is only 11. So let's go about adding the extra 2 on the chlorine, not on the oxygen, because it's happy with a charge of 0 here if we go ahead and check the formal charges. And then now let's double check our formal charges again. So on Cl, it is going to be 7 minus 5 minus 4 over 2. And that is going to be 7 minus 5 minus 2, giving us a 0. Oxygen, it is going to be 6 minus 4 minus 4 over 2, giving us 6 minus 6, which is again going to be 0. And so we've minimized the formal charges and the electrons are all accounted for, which means that this is going to be our best structure. Okay, next up, we have strontium hydroxide that is a strong base and completely dissociates into ions in water. We would like to calculate the pOH of 5.9 by 10 to the negative 4 molar of strontium hydroxide and the concentration of hydroxides in a strontium hydroxide solution with a pH of 12.77. And so let's go ahead and write out the dissociation equation. So it completely dissociates into, 2 plus 2 OH minus. Let's not forget our state symbols. An aqueous solution, and then using this we're gonna develop an ice table. And so because of the fact that we know that it's going into completion, if we just put in what we have, okay, so initially we have 5.9 by 10 to the negative 4, as we were told, 0 and 0 molar. And then because it's going to completion, it is going to lose 5.9 by 10 to the negative 4. This is, so the ratios we have here is 1 to 1 to 2. So it's going to produce 1 times this of strontium ions. So this is going to be plus 5.9 by 10 to the negative 4. And twice that for the hydroxide ions. So it's going to be plus 2 by 5.9 10 to the negative 4. And so this is going to be left with 0 at equilibrium. This is going to be left with 5.9 times 10 to the negative 4 molar at equilibrium. And this is going to be left with 1.18 by 10 to the negative 7. Sorry, negative 3. And then let me just ensure that that is correct. Okay. And so we know that the concentration of hydroxide ions at equilibrium is going to be 1.18 by 10 to the negative 4 molar. We also know that pOH is going to be the negative logarithm of this. So let's go ahead and calculate pOH. The reasoning for this is because we're trying to find the pOH. In the scenario where we're trying to find the pH, we just need to note that pH plus pOH is equal to 14. So the pH would be equal to 14 minus pOH. In this scenario, we're just going to stop at calculating pOH. So let's go ahead and take the negative logarithm of what we have, 1.18 by 10 to the negative 3 molar. And that is going to give us an answer of 2.93. If you plug that into your calculator, and that will be your final answer. In the scenario where they had asked for the pH of this solution rather than the pOH, you just do 14 minus 2.93, and that is going to give you your pH of 11.07. They typically would ask for the pH because that is what we're more used to finding in the lab than the pOH. Okay, for our next question, we want to find the concentration of hydroxide ions in a strontium hydroxide solution with a pH of 12.77. So we're going to be making use of the same equation. So first off, we know that, as stated before, pOH is equal to the negative logarithm of OH. But in this scenario, we're trying to find the concentration. And so we just note that we're isolating this. And so in order to go about that, the equation would become that the concentration of OH ions is equal to 10 to the power of the negative POH. And so we're given the pH, which is equal to 14 minus the POH. So in order to get the POH, we are going to do 14 minus the pH. So let's go about that. 14 minus 12.77, which would give you a POH of 1.23 would be a POH. And so to get the concentration of hydroxide ions, it's going to be 10 to the power of negative 1.23. And that is going to give us a final answer of 0.0589 molar. And that's going to be our final answer. Next up, we're looking for the Lewis structure of IF4. And so just a quick algorithm on how to find the Lewis structure. So first off, we want to determine our central atom. It will usually be the one that can make the most bonds. And so to figure out how many bonds an atom can make, you simply do the calculation of 8 minus the valence electrons, and that will give you the number of bonds it can make. And so let's go ahead and do that. If it's I, it's going to be 8 minus our valence electrons for I, and that is going to give us 7. So ideally it would make 1 bond, and the same thing for fluorine, it's going to make 1. So in this scenario, it's not clear which one is going to be our central atom, but the one that we have less of in the scenario is going to be our best central atom, because that just logically makes sense. And so our structure would look something like this. For our next step, we are going to want to logically arrange your atoms. So in this question, that is how we got the skeleton. So you just logically arrange atoms. And lastly, we want to account for all valence electrons in a manner that minimizes formal charge and places negative charge on the more electronegative atoms. And so if you go about doing that, let's count our valence electrons first. So it's IF4 minus. So our valence electrons are going to be 7 plus 7 by 4 plus 1. If we label that, that is I, F4 minus. And that is going to give us 35 plus 1, which is 36 electrons for us to account for. Okay, and then, so in our structure, let's go about making single bonds first and filling in any octets. Okay, and so fill in on the fluorine first. And then let's go about counting our electrons. So we have 6 by 4, because 6 on each of the fluorines. plus the H electrons are in the bonds. And that is going to give us 24 plus 8, which is going to give us 32 electrons. We have 36 electrons, which means we're going to have remaining 4 electrons. The best place to place them is going to be on our central atom. Let's go about doing that. And so that is going to give us a structure that looks like this. Okay, and then we can go about checking on our formal charges. For each of the fluorines, that is going to be 7 minus 6 minus 2 over 2. That's just 7 minus 7, giving us a 0. On the central atom, it is going to be 7 minus, we have 4 non-bonding electrons, minus H electrons that we have in each of them. And so that is going to be 7 minus 8, and that is going to give us minus 1. So the I in the center is what is responsible for the negative charge. And so our formal charges make sense, our valence electrons make sense, making this our final structure. Okay, next up we are looking for the Lewis structure of ClF5. So let's go about doing that first. Let's count our valence electrons. 7 from the chlorine, 5 by 7 from the fluorine. And that is going to give us 35 plus 7, so 42 electrons to figure out. Let's go ahead and label that. Okay, and so if we start with just a structure like that as our skeleton, let's go about just labeling with one single bond on each and filling in each of the octets for the fluorines. Okay, and then let's double check all of our valence electrons have been accounted for. And so we have 6 by 5 plus 2 by 5. And that is going to give us, just one moment, 40 electrons. And so we have 2 left over, and it would be best to place those on our chlorine. Okay, and so now we want to double check on our formal charges on each of them, just to ensure everything is making sense. So on the fluorine, we are going to have 7 minus 6 minus 2 over 2, and that is going to give us 7 minus 7, which is 0. On the chlorine, we are going to have 7 minus 2 minus 10 over 2. Which is 7 minus 7, so again 0. So the formal charges make sense, valence electrons are all accounted for, and this structure is possible because chlorine is allowed for an expanded octet. So this is going to be our final Lewis structure. For our next part, we want to find out the molecular geometry before we go about finding the electron pair geometry. And so for our molecular geometry, let's find out how many electron pairs the central atom has around it. So it has 1, 2, 3, 4, 5 in bonding pairs, and an additional 1 pair that is a lone pair. And so it has a total of 6 pairs attached to it. And so if we pull up the VSEPR chart, we see that we have 6 pairs around it, so we're going to come to this row, but we have 1 lone pair. And so what this means is that our molecular geometry, so let's just write down a tabularization quickly. So it has 6 electron pairs. And so that is going to be sp3d2. And so if you just add up all of the powers, it should add to 6. So 1 plus 2 plus 3, and that's going to give us our 6. And so this means that the molecular geometry is going to be octahedral. But then our electron geometry is going to account for the fact that we have one lone pair, and so it's going to be square pyramidal. And so you can think of molecular geometry as you're ignoring the fact of whether it's a bonding pair or a lone pair. And so generally the shape would look like an octahedral shape, but then because it's a lone pair, because you have one lone pair, if you're only looking at the bonding pairs, that would look like a square pyramid with the 2 electrons on the bottom, as you can see here. And so these are our 2 answers. Molecular geometry is octahedral, electron geometry is square pyramidal. What that just means is that you have one lone pair here, and that's going to affect the other angles, making them a little under 90 degrees rather than the optimized 90 degrees in the octahedral shape, just because of the lack of symmetry in the electron repulsion. And so those are our 2 final answers. Our next question, we want to answer what is a nonpolar covalent bond. And so to answer this, we need to think of what a covalent bond is in the first place. And covalent bonds are created by sharing of electrons. And so the electrons are at a point that is practically right between the 2 atoms, then what you're going to have is a nonpolar bond. So nonpolar is when sharing is roughly equal. And then that means that polar is when sharing is not equal. How you can tell how much sharing is going on will be entirely dependent on the electronegativity of bonding atoms. And so just to define electronegativity, to jog your memory, that would be the tendency of an atom to attract electrons to it. And so now a good example would be in the oxygen covalent bond. Because they're the same, they have the same electronegativity, so they tend to pull electrons to themselves equally, which means that indeed the electrons will be shared equally. So this would be a good example of a nonpolar bond. But now in the case of water, where oxygen has a very high electronegativity while hydrogen's is lower, that means that oxygen will tend to pull the electrons more towards itself than the hydrogens, and that would cause the electrons to be shared non-equally, so they're going to be closer to the oxygen than the hydrogen. What that is going to cause is partial charges on both of them. So the oxygen will gain a partial negative charge just because the electrons are closer to it, and the hydrogen will gain a partial positive charge because the electrons are further from it. And so this will be a polar bond. All of this can be well described with electronegativity. And so if the difference in electronegativity is over 1.7, you're going to get an ionic bond. So that means the electrons will just straight up be taken away from the less electronegative one, and you're going to get ions. If the difference in electronegativity between the two is between 1.7 and 0.4, you're going to get a polar covalent bond. And so that would be like water. And then in the scenario where the difference in electronegativity is under 0.4, you're going to get a non-polar covalent bond. And so that is like in the scenario of O2, where the difference in electronegativity is 0, which is less than 0.4, so you have a nonpolar. So that's what I meant by the roughly equal, because you're allowed a difference of 0.4. And that is going to be your final answer. Okay, so for our last question, we want the Lewis structure of acetylene and whether we expect the bond to be longer in C2H2 than in C2H4. Compare the energies of the CC bonds in the two, and is it polar or non-polar? So first, let's start by getting the Lewis structure. So for C2H2, you can quickly tell that this is going to be an alkyne that generally have the formula CnHn. And so let's just draw our general structure here. If we start by single bonds, that would imply Marlyn electrons on the carbons. Carbons love to make up to 4 bonds. That's why they're so great for organic chemistry. And if you count the valence electrons, would violate it, because we have 2 by 4 plus 2, which is going to be 10 electrons. And so we have 2, 4, 6, and we would need 8 more electrons on each of them, and that would be over our 10. So let's start with a double bond between the two carbons, because the hydrogens can't make any double bonds. And so again, the carbons are not yet happy. And if we add 2 electrons on each, that'll be 2, 4, 6, 8, 10, 12, which is over our 10. So let's fix this problem by adding another bond between these two. And we have 2, 4, 6, 8, 10. So everything is happy here. Formal charges. On carbon, you would have 4 minus 4, which is 0. And on hydrogen, you would have 1 minus 1, which would give us a 0. So everything is happy this way, and this is going to be our Lewis structure. Next up, we are asked whether the CC bond will be longer in C2H2 than C2H4. And so we need to talk about what dictates how long a bond is. And that actually goes back to the concept of the bond order, which is going to be the number of bonding electrons minus number of the anti-bonding electrons over 2, and this is involved in MO theory. But in organic chemistry, we can quickly see here that it forms a triple bond here, and so the bond order is going to be a high bond order. Then in the case of C2H4, which is just a double bond in between them rather than a triple bond. So this bond order is going to be higher than this bond order. And we know that the higher the bond order, that means the higher the bond energy, which would mean the shorter the bond length itself. So this means that the bond, since the bond order is higher in this case, that means the bond length will be shorter in this case because they have a higher energy, so they must be closer together. So the triple bond in acetylene is shorter than the double bond in ethene. And so the next question is compare the energies of the bonds. And so the energies we've already described here with the bond order. This is going to have a higher bond energy than this one because this has a higher bond order than this one. And lastly, we want to answer, is it polar or non-polar? This is a linear molecule, and you would have the dipoles pointing inwards, and thus they would both cancel out because the dipoles will be equal. In this case, the dipoles would look like this. And so they all cancel. This one cancels this, and this one cancels this. And so both are going to be non-polar. And those are your final answers. Okay, and those are all of the questions that I have for you today. I hope you enjoyed today's Q&A. If you'd like to be notified when we do post more videos on the OneClass channel, be sure to hit the subscribe button and the bell right next to it. If you'd like to be able to post questions of your own so you can see them answered on the live stream, be sure to check out the links in the description to the OneClass page. This has been Marlyn from OneClass, and I hope to see you next time.